Let us begin our optimization journey with very simple example. Here our objective is to construct the bridge which can withstand the load of 1 e raised to 5 Newton. This load we are going to apply at the top and the two ends of the bridge we are going to fix. The overall dimension of the bridge is shown in the image. As of now we absolutely don't have any idea how the bridge is going to look like. But we know for sure that this is not the optimized shape. So let us see how we can perform the design optimization and how it will give us the results. Once we are in the Ansys Workbench, first thing that we are going to do is the static structural analysis. So simply go to the toolbox and here let us double click on the static structural. Though we can create the geometry in the design modeler as it is very simple, still for this session to save the time I will import the bridge.stp file. Let us go to the mechanical window to apply the loads and boundary conditions. Since in the beginning itself we know that we are going to perform the optimization, here while creating the mesh we are going to by default create very fine mesh. So let us first create the mesh by using the default setting and see how much refinement we are going to need. So as of now the mesh looks very coarse. So again click on the mesh and instead of element size to be default, let us set 10 mm. Here the 10 mm element size looks sufficient. But still if you want to spend less amount of time in extracting the geometry, here you can put more refined mesh. But as of now I think 10 mm is the optimum one. Now let us apply the load and boundary condition as per our problem statement. Under the solution, let us request total deformation and the stress. As of now, though we are not exclusively looking for any values, but still it is good to have them. By default, when we construct the bridge like the block, you can see the total deformation that we are getting is around 0.03 mm. Now let us see how we can do the optimization. First, close the mechanical window to limit the licenses. Once the static structural analysis is done, from the analysis system itself, you will have to look for topology optimization. Just drag and drop the topology optimization on the solution of static structural. So what it will essentially does is that it will take the solution from static structural and it will apply to the topology optimization. Now let us go to the setup window of the topology optimization. If you carefully look, even if we are in the topology optimization, the interface will be exactly same as that of the mechanical window. Under the topology optimization, you will get three regions. First and very important that we have is the objective. As we have already seen, objective is nothing but goal of optimization. What exactly we want from our analysis. So currently my objective has been set to compliance and I want to have this compliance as minimum as possible. But let's say instead of compliance, I want to have the different parameter. For example, I want to have the stress value below particular limit or I want to minimize the stress value. Then you can use the response type as a stress also. But as of now, our primary interest is to minimize the compliance or maximize the stiffness. So let us do that. So here I will set it to compliance and the goal will be minimize one. Next important thing that we have seen is the design constraint or the response constraint. So these are the values which will get changed in order to achieve our objective. So under the restraint constraint, what I am basically saying is that I want to have the response in terms of mass and I want to retain the mass of 50%. With this problem statement, what optimization will essentially does that it will reduce the mass which are not contributing to the load bearing capacity. Another interesting thing is the design space. So in the Ansys Workbench, that design space is known as an optimization region. So by default, this optimization region has been set it with respect to the all bodies, and under the exclusive region you can see currently it has been set as all boundary condition. And this is very interesting. When I say optimization region, basically within that region Ansys Workbench will either add or remove the material, that we know for sure. But here is the interesting thing. Let us say we have this particular assembly and through these edges it is getting fixed with the other assembly. So does it make sense that he will remove the material from this location? Well, even if it does, then it will not be a practical solution because then there will be no place to connect it to the other component. Same goes with the load application point also. We are applying the load at this location. That means the load is coming from some other component. So under the optimization region, if we include this region also, then again this will get changed and it will not be a practical one. So under the optimization region, we will make sure to set the exclusive region as the boundary condition. So it will not modify the location where the boundary condition have been applied. Once we get the result, you will see how the optimization shape will look like. So I think all the three things have been said. First one is the optimization region. Second one is our objective, which mostly we are going to keep it to compliance, and goal will be to minimize it. And keep in mind, the compliance is nothing but inverse of stiffness. And last thing is the response constraint through which we are going to achieve our objective. Now click on the solution and right click and you can simply solve it. But prior to solving it, let me insert some of the output. So under the user defined results, let me insert it to the topo. So what this output essentially does is that it will give the pictorial or contour wise representation from where he have removed or added the material. Similarly, let me add another result. So here itself I will say duplicate. And instead of topo, let us set it to eTopo. So with the eTopo, with the element wise, it will give you the density. Now simply right click on solution and set it to solve. Since it is optimization problem, it usually takes lot of iteration to solve our problem. By the way, you might have seen the ancient bridge in your cities. Those bridges will typically have the arch-like shape. So let us see whether our optimization is giving shape like that or not. If it gives us that shape, that means our ancestors were truly smart. Once the analysis gets solved, let us cross our finger and see the results properly. Click on the topology density to see the result. And you can see we are getting the typical arc-like shape. So our ancestors indeed were truly smart. You can play the animation to see how the material is getting removed. You can see at the top, currently the red color is removed, which has been set it to 0 to 0.4. Marginal is the 0.4 to 0.6 and the keep is with the 0.6 to 1. So with the keep, definitely all the boundary conditions are included. You can click on the user defined results to see the same thing but in the contour wise. So here you can check out, 1 means he is not going to remove the element and with the 0 he is going to remove the element. So at the end of our optimization, when our response constraint has been set to 50% or he has retained the mass of 50%, then we are getting the shape like this. Let us push our optimization to its limit. Under the response constraint, let us say just retain the mass of 20% and see what kind of optimized shape that it will give us. Okay, once the analysis get completed, again click on the topology density. So you can see these are again typical kind of shape that you have seen in the bridges also. It looks nice, isn't it? Under the topology density itself, there is another option which is known as a retain threshold. So far, it is retaining all the material or the element which has the value more than 0.4. So if I say, okay, retain all the elements which also has the value of 0.4, then you can see he has added some more element. But instead of 0.4, if I set it to 0.8, then you will see that he will remove most of the material. Or you can also say element, because technically the factor of 0 to 1, it is getting applied to the element only. But physically the material sounds good, so I am saying material. But as of now, let us put this value back to the 0.5. What I am essentially trying to say is that you can interpret the optimization results in multiple ways. As of now, the optimization has given us this shape which has the minimum compliance, and with this shape we are able to reduce the mass by 80%. But at the same time, you will have to think in terms of manufacturing perspective also. Whether this shape is manufacturable or not, you will have to ask yourself. Another thing is that we will have to do the design validation to check whether this shape is giving appropriate results or not. So let us see how we can do the design validation. Let me just close this window. Now in order to start the design validation, right click on the results and here set it to transfer to design validation system geometry. Once you right click on it, it will create another system of design validation, but it will take typically more time. Once this system have been created, you will have to follow the step-by-step procedure now. First thing, right click on the results and set it to update. First we are going to update the results from the topology optimization. You might say, but we just did it. But again, since we have created the validation system, we will have to update it again. Once you get the green tick on the results, let us again right click on the geometry and set it to update. Keep in mind, first thing you have to do is to update it. Once it gets updated, you will get the green tick in front of geometry. Since generally the output of topology optimization is in the STL format, we generally don't recommend to use the design modeler, or you can't even use the design modeler to make the modification in the STL file. So what we will do is that we will go to the space claim modeler. Simply right click over here and set it to edit geometry in the space claim. Before going into the geometry modification and extracting the CAD from the STL file, let me be clear on one point. Generally, when you work in the organization, you will do the topology optimization on the complex component. So at that time, from the CAE analyst perspective, it is not possible for us to extract the complicated CAD from the STL file. In those cases, rather than spending lot of time on extracting the CAD, you can simply give this STL file to the design engineer. Design engineer will have the sophisticated tools such as NXCAD, SolidWorks, Creo or CATIA. Using those tools, it will be very easy to extract the faces and create the geometry very fast. But since you should have idea about the space claim modeler also and the procedure to extract the CAD, we are going to do this exercise. So under the structure, you can see we have two files. One is the SYS1, which includes the original block, and other one is again SYS1. So here let me rename it. Give the appropriate name to the CAD. Again let us click on it. Another thing that you might have noticed, currently here we are getting this typical symbol which is saying that this is not an activated part. So in the end we are going to make it activate, but keep in mind we will have to do it, otherwise it will not appear in the mechanical window. So let us begin to understand the procedure through which we can extract the CAD. First thing, we don't require the original CAD, so I will just hide it. Second thing that we are going to do is to check whether there are some errors or warnings with this CAD. So simply we want to check the problem. Click on the facet and again click on the check faces. Once you click on the check faces, simply select the CAD or the geometry or the faces onto which you want to apply this operation. Once you select it, under the message it is saying no geometry problems were found. So this is one sign of relief. Again set it to close. Once that has been done, you can again go and take the individual check, such as you can check whether there are some problems with the hole, edges, over-connected regions or the sharp edges. So let us quickly do that so we will not regret it later on. Simply click on these holes and select the geometry. As you can see, under the information it says no areas were found. Now let us do the same thing for the intersection also. Select it. So you can see if the blue color is coming, that means there is no problem with the intersection. If there is some problem, it will show you in the red color. Again let us do it and check it for over-connected region. So you can see currently no areas were found. Now let us do it for the fixed sharps also. Select it and you can see currently it shows that there are 8 areas have been found. But if you carefully see that those 8 areas are nothing but our boundary condition areas. So I am not going to change it and I will keep those as it is. Once the geometry have been checked properly, now we are in good shape to convert our facet representation into solid one. So just right click over here, set it to convert to solid and set do not merge faces. This particular pop-up is coming because the space claim is not that good to handle the large assemblies. But since we have the simple component, I will simply say yes. As you can see, previously at this location we had the facet representation. But now we have the solid representation. But still, this solid is not activated one. So just right click over here and say activate for physics. You can see that currently cross symbol has removed. Now again switch this on and let us go to the mechanical to apply the loads and boundary conditions. Once the mechanical window get open, you can check out the warnings. Currently under the message it had given me one warning. So it basically says the one or more objects may have lost some of the scoping attachment. And if you check, currently in front of geometry there is a question mark. So this geometry basically have lost their material. Now right click on the bridge and here I will set it to hide body. So this particular bridge free part I don't want because this is the original part and not a optimized one. So simply I am going to suppress this part. At the same time, let us apply the material to the optimized bridge. Under the assignment, select it and set it to structural steel. For the meshing, let us create the default mesh. Once the meshing get completed, we will have to scope the force and fix support again. So on the force, set it to geometry. Let us switch on the face selection filter and select the particular face. So here, since it is prompting me to select the element, I will select few element and under the element I will set it to limit. So automatically the entire face will get selected. Same goes with the fix support. Once we have both the edges selected, now let us again go for apply and let us right click on the solution and set it to solve. Let us go to the solution and observe the total deformation and the stresses. So primary, our focus will be on the total deformation. Simply click over here and set it to play. If you remember, previously we were getting the displacement as 0.03 mm, but now we are getting the displacement of 0.1 mm. So technically the displacement has indeed increased. But if you think about it, our objective was to minimize the weight and not the displacement. So I hope at the end of this session you have understand how we can perform the topology optimization. In the subsequent session we will also see how we can apply the response constraint in terms of the displacement also. But till then, take care, goodbye.